Welcome back to Carneades.org. Today we're going to be continuing with our series, 6 months of set theory and higher order logic. This is month number 2, looking at operations and relations of sets. Stay tuned for a brand new video on set theory every single day for the whole month of October. In this video, we are going to be doing a gigantic proof. The proof that all Cartesian products are sets. Now, in this video, we're going to look at a proof of the claim that all Cartesian products of sets are also sets themselves. The specific claim that we are going to prove is for all A and all B. A is a member of V, the universal class and therefore a set, and B is a member of V, the universal class and therefore a set, implies that the Cartesian product of A and B is a member of V. This is a tough one. If you want a hint, keep watching, or feel free to pause here if you want to try it for yourself. As a warning, this will take a lot of work given the theorems that we have already. It'll be a little bit easier if you assume a theorem that I'm going to prove here, just because we haven't proven it in the series, but is quite intuitive and sensical to have in your arsenal. So, with that, one way to prove this is to prove that the Cartesian product of A and B is the subset of something that we already know is a set, and therefore must be a set by axiom 2. This is the method that we're going to use here. First, we're going to show that if A and B are sets, then the power set of the union of A and B is a set as well. Then we will show that the Cartesian product of A and B is a subset of the power set of the union of A and B. Try it yourself now for a good challenge, or keep watching for the full proof. Now, this is likely the longest proof we've ever done on the channel. So before we go into it, I'm going to give you some guideposts to help you follow along if you get lost in some of the details. We'll start with an indirect proof, assuming the opposite of the conclusion and showing it leads to a contradiction. The negation of our conditional, that's our conclusion, leads to the affirmation of the antecedent and the negation of the consequent. So we're left with two sets instantiated as C and D, which are both members of V, the universal class, but whose Cartesian product is not. We'll show that this is impossible because it leads to a contradiction, and therefore the implication that we're talking about must be the case. So that's just premises 1 through 6 is the beginning of that indirect proof. Our next order of business is to show that the power set of this union of C and D is a set. This is harder than it seems since we are missing a crucial rule, which we have referenced and talked about when we talked about unions of classes and sets, but we never proved it, and we never explicitly stated it as part of a definition. This is the rule that the union of C and D is identical to the union of the class CD. Like I said, we talked about it, but we never proved it. Once we have that, it's a simple matter of using the power axiom twice to get that as a set. And, of course, the union axiom. So, premise 7 through 14 show that if C and D are sets, then so is the union of C and D. And from premises 15 to premise 80, we show that the union of C and D is identical to C union D using an indirect proof. We do not necessarily need to do this for the proof, but it will come in handy in other proofs to have this as a general rule. Once we have shown this, it's a few steps to show that the power set of C union D is a set, premise 81 through 86. Next up, we show that the Cartesian product of C and D is a subclass of the power set of CUD. To do this, we're going to break down the specific definitions of each of these terms and show the conclusions that they lead to. It takes a while, and it takes a number of indirect proofs. We almost run out of variables. But we see that it must be the case that the Cartesian product of C and D is a subclass of the power set of CUD. From premises 87 to premise 178. Whew, but we're not done yet. Once we've done that, we can use axiom 2 to show that the Cartesian product of C and D must be a member of V. And therefore, our initial assumption leads to a contradiction, and so we can affirm the conclusion. Whew, that's a lot of work. If you want the specifics, follow me, and let's go. So, our conclusion is that for all A and all B, if A is a member of the universal class and B is a member of the universal class, that implies that the Cartesian product of A and B is a member of the universal class. So as we said, we're going to get started with an assumed indirect proof. We'll use change of quantifier to bring that negation inside, existentially instantiate A and B to C and D. And then we'll go ahead and break this implication down as we often do, turning it into a disjunction, distributing the negation across and changing that to a conjunction and using our double negation, and then simplifying out one of the elements of that C is a member of the universal class and D is a member of the universal class. Then we'll go ahead and use axiom 4 and universal instantiation to show that if C is a member of V and D is a member of V, that implies that there exists some Z such that Z is the set of C and D and Z is a member of V. Then using modus ponens, we can get the second half of that only. And then existential instantiation of Z will get us E is equal to the class C, D, and E is a member of V. We can simplify that out to just E equals C, D, and E is a member of V. Then through identity, we can have that the class of C, D is a member of V, because we have E is a member of V and E equals C, D. Then we'll go ahead and universally instantiate A5, which is our union axiom, to show that if CD is a member of V, then the union of CD is a member of V. This gives us the union of CD is a member of V through 1213 modus ponens. Now, in order to prove our conclusion, we need to show that CUD is equal to the union of CD. You might be able to do this proof, and you probably are, without actually proving this statement, but we're going to prove it here so we have it in our arsenal for later because it's quite a bear to prove. It seems very simple and intuitive, but it's going to take some work. So, with that, we're going to go ahead and deny this claim for an assumed indirect proof. So it's not the case that the union of C and D is equal to the union of the class of C, D. Then we will use our relative union definition to pull this out and say, okay, we have our identity now, but what does that really mean if those two were the same? We are denying that, and so using identity, we can deny the second half of that. So we're denying that for all A is a member of the union of C, D is materially equivalent to A is a member of C, or X rather, excuse me. For all X is a member of the union of the class of C, D is materially equivalent to X is a member of C, or X is a member of D. From this point, it's really obvious that this is going to fail because that's just the definition of unions. But it's going to take a lot more premises to prove this wrong. So we'll use a change of quantifier to pull that negation in, and then we'll deny this big material equivalence by existentially instantiating X to F. Next up, we're going to do the definition of an absolute union to get exactly what this is. So the union of CD equals the union of CD means by definition all of this. We use identity to prove the first half of that statement, and then use identity to put that in its place so that we have the second half of the statement. For all X is a member of the union of CD is materially equivalent to there exists some Y such that X is a member of Y and Y is a member of the class of C, D. We can also universally instantiate 22 to F. We want this same variable, and because we're using universal instantiation here, we can do it. F is a member of the union of CD, because we have that in the earlier premise, is materially equivalent to there exists some Y such that F is a member of Y and Y is a member of the class of C, D. All right, moving on to a new page. We have to bring some premises with us. We start by bringing the beginnings of our assumed indirect proofs, and then some useful premises that we'll need later. So, we have 23 Universal instantiation is what we just did. Then we're going to spread out this equivalence because equivalencies are just two implications. And then we'll simplify that down to the implication of if F is a member of the union of the class CD, that implies that there exists some Y such that F is a member of Y and Y is a member of the class CD. And we'll also simplify the other half of that implication, just for good measure. Now, we can also take premise 19 and use material equivalence. It's important to note what we're doing here, because this is not how I at least usually use material equivalence. There's two things you can do with material equivalence. You can pull it out to two implications, or you can pull it out to a disjunction of two conjunctions, where you're saying either both of these are true or both of these are false. And that's what we're doing here. So it's the same move we did earlier, but slightly different in terms of the product we end up with. Because we're denying this big or statement, we can use De Morgan's rule to distribute that negation across and get a conjunction between two bigger statements, and then simplify those out to the two halves. We'll then use De Morgan's rule again on 29 to distribute our negation, and we turn it back into a disjunction. And so we have a kind of double disjunction here. And on that, we'll turn it into an implication, taking our negated first half of the disjunction, turning it into being not negated, and change it to an implication, leaving the second half alone. Then we will use something that we do not use often, which is hypothetical syllogism. So we have in 26, we have something that implies F is a member of the union of the class CD. And in 26 we have that. And in 32 we have F is a member of the union of CD implies something else. We can use hypothetical syllogism to stick those two together and get this piece. We then have F is a member of the union of the class CD, or F is a member of C, or F is a member of D from 30, De Morgan's law of distributing that negation across. Whew. Now we're going to use our curly bracket definition to see exactly what CD means, or the class of CD means. We can use identity to get the first half of that, and then we have for all H is a member of CD is materially equivalent to H equals C or H equals D from identity. Now we're going to jump into a new indirect proof because we're going to want to disprove the second half of one of these implications that we have gotten. Okay? So we're going to try to disprove that there exists some Y such that F is a member of Y and Y is a member of CD. We'll use 33, 38 modus ponens to get it's not the case that F is a member of C or F is a member of D. We have the way we set this up, it's nice and it works with modus ponens. Existential instantiation from 38 gets us that F is a member of G and G is a member of C, of the class of CD. This should show us pretty clearly that we are going to be able to get to a contradiction here. But we have to do the work to get it out. So G is a member of the class CD. And starting again on a new page, we'll bring in our premises that will be useful and the starts of all of our indirect proofs. And we were at G is a member of the class of CD from premise 40 simplification. And then we will universally instantiate 37 again to get G is a member of CD means that either G is C or G is D, basically. We'll use equivalence to spread that out and then simplify it down. Given that we have G as a member of CD, that's the direction we want to go. So we have G equals C or G equals D. F is a member of G. And so using De Morgan's law, we can distribute our negation from 39 to get it's not the case that F is a member of C and it's not the case that F is a member of D. We simplify that down to it's not the case that F is a member of C. We're going to do a mini indirect proof here to basically show that this is going to be problematic. So we assume G equals C. F is a member of C. We can get that from identity. From 46 and 49. And therefore, we have a contradiction because it's not the case that f is a member of C and f is a member of C. This means we can pull out from our indirect proof it's not the case that G equals C, but G isn't going to be able to equal D either. So we use disjunctive syllogism to get G equals D. Once again, use identity to get f as a member of D, but f can't be a member of D. So we can join our two contradictory statements, and we can pull another step out of this indirect proof to show it's not the case there exists some y such that f is a member of y and y is a member of the class of CD. Whew! Next page. Let's keep going. So we'll bring in some useful premises from before. And here's the conclusion of our indirect proof that we just proved. So, as I said, we're going to use that on an implication we had earlier, all the way back up in premise 25, to deny f is a member of the union of the class of C and D. And this will let us use 34 and 58 disjunctive syllogism to get either f is a member of C or f is a member of D. If we take 57 and we change the quantifier there, we get for all y. It's not the case that f is a member of y and y is a member of the class of CD. We universally instantiate this in, distribute our negation to get a negated disjunction with De Morgan's law. And then we'll take 37 and universally instantiate it so that we can get C is a member of CD is materially equivalent to C equals C or C equals D. We can clearly get the second half of that by saying C equals D by identity, adding on C equals D. Then when we pull that out for equivalence and simplify it down to the equivalence in the direction of the first half that we have, the antecedent that we have, we can get C is a member of CD. Pretty obvious, but takes a couple steps to prove. Then through disjunctive syllogism with 62 and 68, we have it's not the case that f is a member of C, because we've shown that C is a member of CD, so the only way for 62 to be true is if it's not the case that f is a member of C. And therefore, from 59, 69, f must be a member of D, because f had to be a member of one of them. But this is going to run into the same problem. We're going to go through the same process we just did with C and show that D must be a member of CD. And moving on once again to another page, we have D as a member of CD, which means that it's not the case that when we universally instantiate, it's not the case that f is a member of D and D is a member of CD. We can distribute that across through De Morgan's law, but the problem is we have that D is definitely a member of the class of CD, so it must not be the case that f is a member of D. So it's not the case that f is a member of D and f is a member of D. This is another contradiction from 70 and 79, leaving us with, C, the union of C and D is equal to the union of the class of C and D. A lot of work to prove something that's pretty simple. We're going to hold on to this, because we didn't need to pull from anything else related to this proof, as a rule for the future, that for all A and all B, the union of A and B is equal to the union of the class of A, B. We'll call it union conversion theorem. With that in our bag, we're going to move back to what we were working on for the main part of this proof, which is looking at trying to show that all Cartesian products of sets are sets. And so we're going to take the claim that the union of C and D is a member of V, which we can now conclude from 81 and 14. Then we'll use axiom 6, the axiom we just learned about, the power set axiom, or the power axiom, to show that the power set of the union of C and D is also a member of V from modus ponens. And then we'll show that the power set of the power set of CUD is a member of V, once again using axiom 6 and modus ponens. The reason that we're doing that is because the power set of CUD has as one of its subclasses the Cartesian product of C and D, which is what we're going to show here. So, the assumed indirect proof is it's not the case that C times D, or the Cartesian product of C and D, is a subclass of the power set of CUD. Because if that were the case, then we could prove it's a member of the universal class. We're assuming that it's false, showing it leads to a contradiction and moving backwards. So we're going to go ahead and use our subclass definition to show exactly what this means and kind of pull that out because we have that identity from the beginning, using identity to get a denial of this universal quantifier. We'll bring that in with a change of quantifier. It's always great to have those denials of universally quantified implications because they give us two solid halves to work with. We'll existentially instantiate that. We'll bring our premises along for the ride, and then we'll use implication to split the implication and get a disjunction. When we have a negated disjunction, that's great because we can use De Morgan's law to spread those negations across and double negation to clean them up. And we have a conjunction that we can simplify down to its two halves. So we have I is a member of the Cartesian product CXD, and it's not the case that I is a member of the power set of C union D. So these are the two halves that we're going to show when brought together lead to a contradiction. Now, in order to work with Cartesian products, we have to break them down into their definitions, which is going to be a lot of work because we're also going to have to break those further down into the definitions of our ordered pairs, but we'll start with the Cartesian products. So, in order to understand what we mean by the Cartesian product of C and D, we use this definition through universal instantiation. We, of course, have CXD is equal to CXD. And so for all J is a member of CXD is materially equivalent to, there exists some K, there exists some L, such that J is equal to the ordered pair KL, and K is a member of C, and L is a member of D. We'll, of course, instantiate J to I, because I is what we have in that first half. And then we'll use equivalence. This has to go onto two lines because it's a monster of an equivalence with those two implications. And we'll simplify that down to the one that we have. We have that first half of I as a member of CXD, so that's the one we want. We'll use modus ponens to get there exists some K, there exists some L, such that I is equal to the ordered pair KL, and K is a member of C, and L is a member of D. Then we'll go ahead and existentially instantiate K and L to M and N so we can work with them a little bit better. And then simplify this down to I equals MN. In order to figure out, once again, I said we were going to have to define our terms again. We have to break down those angle brackets once again to curly brackets using our angle bracket def or our ordered pair definition here. And using identity to show exactly what I equals. We're also going to simplify 103 down to the statement M is a member of C and N is a member of D, which will be useful later. Now that we've done that and we've gotten some of the pieces out of kind of one of the halves of what we're working with, we're going to take a look at the other half, the power set half, and do our power set definitions to break this down. So we have the power set of CUD equals the power set of CUD equals, by definition, this long string of what we mean by a power set, to kind of shave off one of those power sets. We have those two things equal themselves, of course, by identity. And so we can conclude this for all O. O is a subclass of the power set of CUD is materially equivalent to O is a member of the power set of CUD. Now, moving on to a new page, we have... So now we're going to continue by universally instantiating O to I again, because I, we want that to carry through, so it's easy to pair back up and to show that these do lead to contradictions. Premise 111 equivalence, we'll break that equivalence down and once again split it out into an implication. We don't have the first half of this implication, but we do have the second half from 95 back in the original thing we split up, so we can show it's not the case that I is a subclass of the power set of CUD. And what that means is when we take our subclass definition again, I is a subclass of the power set of CUD equals, by definition for all P is a member of I implies P is a member of the power set of CUD. We'll use identity to pull out that second half and negate it from 114, 115, an identity. Once again, we'll go through our normal process with a negated universally quantified implication where we'll use change of quantifier, existential instantiation, implication, De Morgan's and double negation, and finally simplification to get Q is a member of I, and it's not the case that Q is a member of the power set of CUD. We'll use our curly bracket definition to break and universal instantiation to say what we mean by I is equal to M and Mn, which we had back from 106, so now we're starting to bring these halves closer together. And through that, we will show that for all R is a member of I is materially equivalent to R equals the class of M, or R equals the class of Mn. And we will universally instantiate that to Q. That's why we had to kind of switch off, because Q was going to get existentially instantiated. We had to get it as a variable before we could use this. So we will show that Q is a member of I is materially equivalent to Q equals the class of M, or Q equals the class of M and N. This is not using universal instantiation. That's incorrect. It should be 125 equivalence. We'll split up that using an equivalence of the two implications in both directions. We'll take this half of the implication that we already have, because we already have Q as a member of I, and we'll show that either Q equals the class of M or Q equals the class of M and N by modus ponens. 121, 127. Whew, we're getting there. It's long, but we're getting there. So, now that we have that, we're going to go ahead and continue to break down our power set. We kind of have to seesaw back and forth between these two sides of showing what the implications are for each. So we're going to break down another level of the power set on the power set of CUD. So it's not the case that Q is a member of the power set of CUD, so it's going to be useful there. So we, of course, have the power set of CUD equals the power set of CUD. So we can get the second half of that through identity. We're, of course, going to instantiate S as Q, because that's what we have. We have it's not the case that Q is a member of the power set of CUD. And so we'll use equivalence to pull these two apart, and we'll take the one that we can deny the consequent of, because we can use modus tollens on that. Using modus tollens, we get it's not the case that Q is a subclass of CUD. And once again, we will use our subclass definition to see what we mean by that. That means, by definition, for all T is a member of Q implies T is a member of CUD. So, using identity, we negate the second half of that, because we have shown in 135 that it's not the case that Q is a subclass of CUD. So that means it's not the case that the second half of that. Now we have, once again, a denial of a universally quantified implication, which are great because they allow us to split up into two simplified conjunctions. So we use change of quantifier, existential instantiation, implication, De Morgan's law, double negation, as we always do, and finally simplification to get U as a member of Q. And it's not the case that U is a member of CUD. Whew! What has all of that really gotten us? Well, we have one more step to do, one more thing we need to break down. We need to define what we mean by that relative union in there. So when we say U is a member of CUD, what do we mean? Well, once again, we can just use identity to get for all W is a member of CUD is materially equivalent to W is a member of C, or W is a member of D. If you're following the pattern, you will have guessed what we're going to instantiate W to. But we have to jump to a new slide to do it. Whew! So, we instantiate W to U, of course, because it's not the case that U is a member of CUD. And so we use equivalence to split up those implications. We take and simplify down to the implication that we have the second half of denied. So we use modus tollens again to get a denial of the antecedent of that implication. And we have a denial of a disjunction, which is great because we can then distribute that through De Morgan's law and get two nice, meaty pieces that we can simplify out. So it's not the case that U is a member of C, and it's not the case that U is a member of D. Ooh. It's going to be important. All right, jumping all the way back to 103, we can simplify out, this shouldn't be 103, excuse me, this should be 107. We can simplify out M is a member of C. We're going to use an assumed indirect proof to say that Q is equal to the class of M, and our curly brackets definition to see what that means. Note, we've gotten all the way up to X so far. We skipped V because V has a specific meaning in this world of set theory. For all X, X is a member of Q's material equivalent to X equals M. We have universal instantiation from 157 that U is a member of Q's materially equivalent to U equals M. And so U is a member of Q implies that U equals M, and U equals M implies U is a member of Q. We simplify that down to something we can use. U is a member of Q implies U equals M. U equals M by 142, 160, modus ponens. U is a member of C by 154, 161, identity. And therefore, it is the case that U is a member of C, and it's not the case that U is a member of C, meaning that we have arrived at a contradiction. So on our next slide, we can deny what we initially started with, which was Q is equal to the class of M. So it's not the case that Q is equal to the class of M. Therefore, by 128 and 164, that should be disjunction, we can show that Q is equal to the class Mn. We're going to do the same thing here. Show what does it mean if Q is equal to Mn, and show it's problematic. We're all the way up to Y. For all Y, Y is a member of Q is materially equivalent to Y equals M or Y equals N. U is a member of Q is materially equivalent to U equals M or U equals N through universal instantiation. Once again with our equivalence, and we'll pull that out as 169 simplification. We have U as a member of Q all the way up in 142, so we can get U equals M or U equals N. Let's assume that U equals M very quickly for a very short assumed indirect proof. Once again, as we showed earlier, U is a member of C from that, and therefore U is a member of C and not a member of C, so U can't be equal to M. So, by disjunctive syllogism, U has to be equal to N. But, lo and behold, can U be equal to N? Well, N is a member of D, and therefore U is a member of D, but U is not a member of D through that conjunction. So, we're left with a contradiction that pulls us all the way out of this. Long indirect proof from 87 to 178 to show that denying the claim that the Cartesian product of C and D is a subclass of the power set of CUD leads to a contradiction. So it must be the case that the Cartesian product of C and D is a subclass of the power class of CUD. Whew. Now that we've shown that, it's not that many steps to our conclusion. So we use axiom 2 universal instantiation to show that if the Cartesian product of C and D is a subclass of the power class of CUD, and the power class of CUD is a member of V, then the Cartesian product of C and D is a member of V. We can conjoin 86 and 179 to get the first half of that implication, and then use modus ponens to get the second half. We, all the way back in premise 5, denied that second half, and we can simplify that out, which means we have a conjunction of two statements that are opposite of each other, also known as a contradiction, which lets us jump finally out of the last level of this gigantic indirect proof to get for all A and all B, A is a member of V and B is a member of V, implies that the Cartesian product of A and B is a member of V, also known as all Cartesian products of sets are themselves sets. Whew! That's our conclusion. QED. I apologize for the typos that existed in there. Hopefully you followed along. I'm extremely impressed if you followed along or did this on your own. Feel free to try to simplify my proof. This is a very long one. I am confident there are simpler ways to do this. But there it is, the proof that all Cartesian products of sets are sets. Whew! Up next, we're going to move to the relations part of this month, where we'll be looking at what are relations and what they are in set theory. Whew! All right. Watch this video and more here at Carneades.org. Watch a new video every single day for the whole month of October. Really, if you do enjoy this content, if you've made it all the way to the end of a 35-minute video of a 185-line proof, please do subscribe, hit that notification bell so you can see more of the content that we're putting out. And stay skeptical, everybody.